In the last video, we saw that the tangent to a curve approximates the curve near the point of tangency. It's not exact though. I have here the function f and a point a, f of a, and its tangent line, and I'm going to mark on the x-axis a value a, and then a horizontal distance away from a, I'm going to call the distance delta x, so that the point on the right is a plus delta x. Associated with that horizontal distance, delta x, there is a vertical distance in the y values of the function. That vertical distance is the change in y, or delta y. So we can say that delta y is the vertical change of the function associated with a horizontal change delta x. Or it's an output change associated with an input change. For that same horizontal change though, the tangent line has a different vertical change. And that vertical change we're going to call, not delta, dy. Note that for either delta y or dy, the horizontal change we're talking about is the same in both cases. And so to associate with dy, we're going to call delta x dx. Now you'll remember that the slope of the tangent line is f prime of a. In general, we can say that f prime of x is equal to dy divided by dx. Now up until now we've only said dy dx. We didn't say divided by, we didn't say over, but now we're saying, hey, it's rise over run. That still doesn't mean, like, just generally speaking, you don't say dy over dx or divided by or anything. Right now though, we're thinking of this as a ratio. We're almost to where we want to be. If I clear the fraction, look, this is a first derivative, dy dx. First derivatives act like fractions. That means I can clear the fraction and I can say that dy is equal to f prime of x dx. Dy is the vertical change for the tangent line. Delta y is the vertical change for the function itself. They're close to each other, not exact. They're approximations. But to wrap up what I just wrote here, I'm going to give you this. Differentials. Dy is the differential of y. Dx is the differential of x. For any particular point on a curve, if I have a dx, a horizontal distance, and an f prime of x, then I can figure out what dy is. I can use that to approximate a change in output for the function. And in order to see this in action, we're going to look at this example. Use differentials to estimate the amount of paint needed to apply a coat of paint 5/10 of a centimeter thick to a hemispherical dome with diameter 50 meters. We see that we're dealing with a hemispherical dome. That's half of a sphere. And this isn't obvious, but we're talking about the amount of paint needed. And if you think about paint, it's in terms of gallons or pints or something, but it's a volume. And the idea is that if I have a half of a sphere and I put a coat of paint on it, that its volume is going to increase just a tiny bit. And that's what differentials can be good for. The volume of a sphere is 4/3 pi r cubed. So the volume of a hemisphere is 2/3 pi r cubed. For the hemispherical dome described in the problem, we have a radius of 25 meters. And the coat of paint, everything else is in meters. We're going to turn this into meters, is 0.0005 meters thick, right? We had to divide by 100. Let's look back at what we have for differentials. Dy is equal to f prime of x times dx. Or in this case, we're going to have that dv is equal to v prime of r dr. dv is equal to v prime of r dr. So in order to figure out dv, we need to know r, we have that. We need to know dr, that's what we just found, right? dr, or we were given that, but we converted that. And now we just need v prime of r. So dV is equal to 2 pi r squared times dr. So in this case, we've got that dV is equal to 2 pi 25 squared times 0.0005. Calculator gives me approximately 1.96, and that's going to be cubic meters. How do I know it's cubic meters? Well, radius is in meters, that's radius squared, and dr is in meters, so that's radius cubed, or meters cubed. So we can say about 2 cubic meters of paint are needed. It doesn't sound like a lot. Check it out though. That's about 528 gallons. I'm going to close by pointing out that what we found was a change in volume, right? dV. And that change in volume was due to the coat of paint. But the deal is that coat of paint changed the radius. And so an incremental change in radius changed the volume. And that's how we figured out how much paint we would need.